Welcome to Control System classes. The topic for today's discussion is Derivative Controller and Proportional Derivative Controller from Electrical Engineering talk. A derivative controller is going to be introduced in the place of a controller. The controller output is called actuating signal. The controller input is error signal. Error signal is notated with E of S and the actuating signal is represented with U of S. As the controller is going to produce output in proportional to the error signal, we can write U of t is proportional to d by dt of E of t. Let us remove the proportional symbol by adding kd. Kd is called derivative gain constant. Take Laplace transform on both sides. U of s will be equal to kd. Differentiation on taking Laplace transform, it will become a product multiplication. So s into E of s. Let us write the transfer function of derivative controller. U of s divided by E of s is s into kd. So we can replace the controller with the function kd into s. So whenever we look at the function kd into s, we can understand that the derivative controller is used there. But the derivative controller will not be used in ideal. It will not be used in separate. It will be always used in a combination along with proportional and integral controller. What may be the reason? We can able to understand that the derivative controller from the name itself, it will act only on rate of change of error. So whenever there is a change in error, during that portion only it will take an action. Whenever we have error, but a constant error, again variable error, constant error, variable error. So it will take only action on rate of change of error and not on constant error. That is the biggest drawback of derivative controller, and hence it will act only on transient periods and not on constant error. That is, it will not concentrate on steady state error. That's why the derivative controller will not be used in separate. It will be used only along with integral and proportional controller. So let us discuss about proportional derivative controller. Here also we can able to understand the output is going to be proportional to the proportional value and the derivative value of error signal. So we have two terms in the expression. U of t is proportional to E of t plus d by dt of E of t. So we have two components here. So let us remove this proportional symbol by adding appropriate constants. So the constant for a proportional is Kp. As both the terms are proportional, for both the terms add Kp constant. Here we have d by dt parameter also. So here we have added another constant Kp into Td. That is Td, where Td is called derivative time constant. Kp is called proportional gain constant. So Kp into Td is called derivative gain constant and it can be notated as Kd. So this term is replaced as Kd here. Now as usual, let us write the transfer function. To take and write the transfer function, let us take Laplace transform on both sides. So U of s will be equal to Kp plus Kd into s into E of s. So we can write the function as U of s by E of s is equal to Kp plus Kd into s. So we can replace the controller block with the terms Kp plus Kd into s, which represents the presence of proportional derivative controller, right? So what is the advantage of using proportional derivative controller? So it will make the system to be stable by changing the transient portions and it will not affect the constant steady state error. Let us verify how it will improve the stability by contributing in the transient portions in the next slide. So here a proportional derivative controller is introduced. Here a proportional derivative controller is introduced, Kp plus S into Kd. Within plant function, it is a general second order open loop transfer function. The general second order transfer function is omega n square divided by S into S plus 2 zeta omega n. Omega n is natural frequency of oscillation, zeta is damping factor. Kp is proportional gain constant, Kd is derivative gain constant. So it is added together. Now the feed forward value is nothing but the product of these two terms, as these two blocks are in cascade. R of S is 1 by S unit step signal. Unity feedback system is assumed. So H of S value is 1. Now, this is my open loop transfer function. Feed forward means you need to multiply both. Let us write C of S by R of S for the given plant function. So, using as it is a negative feedback system, it is the given block is reduced using G of S divided by 1 plus G of S H of S. And from this equation, I have substituted for G of S by multiplying both the feed forward terms, and I had rearranged, and from this I can able to conclude that a 0 was added here. Let us compare the given plant with respect to the given plant equation number 1 with respect to the calculated C of S by R of S, the closed loop transfer function. We can able to conclude here no zeros. The zeros is nothing but the roots of the numerator. But here we have a 0. What is the location of 0? The 0 is S is equal to minus Kp by Kd. It is located at minus Kp by Kd. Right? Similarly, here we have second order system, second order term. Here we have again a second order. Right? Here the damping term is 2 zeta omega n. But here the damping term is increased to 2 zeta omega n plus Kd into omega n square. Right? So it means the damping term is increased now. So we can able to say that the system order remains the same, but a 0 was introduced, the damping factor is increased. So let us revise again, conclude again. So the property, the plant transfer function, this is an open loop. This is a closed loop C of S by R of S after adding a proportional derivative controller. System order, no change in system order, and hence no changes in number of poles. But a 0 was added with proportional derivative controller and the damping factor is increased. Now, what are the consequences of these changes? Our system order is not changed. The stability problem will not be a bigger issue here. But in case of PI controller, we understood it increases the order. So higher order may have an instability problem. So those issues is not occurring in proportional derivative controller. It introduces a 0. We know the effects of zeros. In the earlier videos, I have posted about this. When a 0 was added on the LHS, on the usual time response side, it will increase as the initial overshoot. When a 0 was added on the RHS, it will make the system to behave in the opposite way. It will goes like this. So this is a 0 added in the RHS, the top is with LHS. So because of the added 0, we know the contribution. The contribution is increase in overshoot but reducing time domain specifications. Increases in system damping factor. System damping factor, it means it suppresses the oscillation. It decreases the overshoot. When a 0 was introduced on the RHS, it will create undershoot. But in this example, we have introduced a 0 in LHS, so it only creates an overshoot and not an undershoot. So these effect can be, this overshoot can be decreased by having the damping factor. Right, by having the added advantage of increased damping factor. Even though the 0 contributes the oscillations, it will be reduced, it will be equivalently reduced by increased damping factor according to the value of Kd, what you are choosing in the system. This is an ideal differentiator. Let us realize that proportional derivative controller using op-amp. So this is an ideal differentiator. If it is an integrator, in the feedback part, we will have a capacitor. As it is a differentiator, over the input side, we have the capacitor. So the output voltage will be the derivative of input voltage. Right? When you write in S domain, this will become S into V in of S. So the transfer function for ideal differentiator is minus RC into S into V in of S. So when you adjust RC, you can able to change the output voltage. Right? So this RC is nothing but my derivative controller gain constant. But it is an ideal differentiator. It doesn't include a proportional controller effect. So let us add a proportional controller effect also. As we have proportional derivative controller, we need to add an equivalent resistor in parallel with input resist, in parallel with input capacitor to convert a pure differentiator into proportional and derivative controller. So you can look at the circuit. So here to the original capacitor, now an additional resistor is connected in parallel. So now we have two resistance and capacitor. As it is an inverting op-amp circuit, the first circuit will produce a phase shift. To compensate the phase shift, we have introduced a sign changer. Sign changer input resistance and feedback resistance value will be always equal. So its gain U of t by U1 of t is -1. What would be the gain of first stage operational amplifier? Second stage gain is -1. What would be the gain of first stage amplifier? It is, as it introduces a phase shift, minus of R2 by R1 plus S into R2 plus C1. Let us write for the second stage -1. Overall gain is U of S divided by E of S. Let us take the term R2 by R1 outside. So you can write R2 by R1 into 1 plus S into R1 C1, where R2 by R1 is called KP and R1 into C1 is called TD. So by adjusting these R2, R1 and C1, you can have the control over the gains of the operation. You can control, we have the control over the gains of proportional derivative controller, and hence we can able to achieve the desired values of damping. Let us verify the concepts what we had discussed with MATLAB outputs. So here I'm interested to print 4 outputs. So I have used the command subplot of 2, 2, 1. So it means 2 rows, 2 columns. And first position, I'm going to print the output of second order system, a normal second order system without any added controller. In the second case, I'm using with controller, with proportional derivative controller. I'm applying for second order system. The third case is without controller for first order system, and the first order system I have assumed it is 1 divided by S plus 1. Then the second order for first order system I have introduced a proportional derivative controller. What is the transfer function? What is the syntax we need to use here? If it is a controller, for a controller the command in MATLAB is PID KP, KI, KD. This is a function. Here I'm interested to use only PD controller and not I controller. So in the command, I need to declare KP, 0, KD. So the MATLAB understood that the integral portion is 0, only KP and KD is used. Similarly, the transfer function, to write the overall transfer function of the given block, the command is T is equal to, that is T is my user declared variable. T is equal to feedback of controller into plant, 1, as my plant has an unity, my system has unity feedback system. CLC, clear all, close are all basic commands. To write the program in S domain, I have used the command S is equal to TF of S. I also had used the command step info of the particular transfer function. This step info will print the time domain specifications of the given transfer functions. So let us see the output. Before seeing the output, I have also summarized the results of MATLAB. So this is a transfer function. The transfer function with and without controller is given for both first order and second order. And I have calculated the DC gain manually and also by using the MATLAB program, using DC gain of P1 of S, DC gain of T1 of S, right? So by substituting S as 0, I can able to achieve my DC gain. We can also see here my final value is not 1. It means we have a steady state error. As we have used a derivative controller here, it will not concentrate on steady state portion. It will concentrate only on transient portion, right? So, and hence we have a steady state error here. What is a steady state error value? You can cross check your steady state error value by using the formula ESS is equal to 1 divided by 1 plus KP. This is a steady state error contributed by P controller. 1 minus the value will be the error. And also you can verify here the time domain specifications got decreased, but the overshoot is increased because even for first order system, the overshoot is increased because of adding zeros. So we can also verify the same with the MATLAB output. So only the transient portions get affected, get changed, and the damping is controlled. We have a steady state error always. Thank you.